This lecture covers the sensory pathways in the spinal cord. These will ascend from the primary afferents, arising along the length of the spinal cord, innervating the body, and then projecting upward through the spinal cord. Thus they are the ascending spinal pathways. There are two pathways that you must know because of their clinical relevance, and that's the posterior column medial lemniscus pathway and the spinothalamic tracts. Those are the two conscious pathways, which we'll cover in the first part. Of course, there are additional non-conscious pathways that don't make it to the cortex but still affect nervous system function. We'll go through those in the second part, and then finally we're actually going to go back down the spinal cord because we have to control pain. One of the ways that we control pain is through descending input onto those nociceptive afferents that we'll touch on in the early parts of this lecture. This allows pain to slowly subside over time, itches to become less itchy, and our expectations to affect the degree to which we feel pain. In other words, the placebo effect is created by this central gating of pain. But let's start off with the conscious pathways. Conscious sensation of non-painful sensations are carried through the posterior column medial lemniscus pathway, while pain and temperature sensations are conveyed along the spinothalamic tract. And that is only one of the components of the anterolateral pathway. There are other offshoots that don't make it to the cortex, and so they'll be in the next section. Let's start off with the posterior column medial lemniscus pathway. This tells you it's going to project along the posterior columns, and it will also form the medial lemniscus after synapsing in the medulla. In both of these tracts, there are only 3 neurons that we need to know, so that's not too bad. Of course, we're going to start off in the dorsal root ganglion. These somatosensory neurons are going to innervate a variety of targets, but there's some kind of receptor that the axon links up with, not free nerve endings. We got a few options. It could be muscle spindles. This will tell us muscle length. More on these later. Could be Golgi tendon organs. This will tell us tension in the tendons. Could also be some encapsulated receptor in the skin. This will tell us about skin stretch, vibration, things of that nature. All of these are non-painful stimuli, and thus they're going to be conveyed along the posterior columns. Alright, let's see if I can do this post hoc here. Posterior columns in the back. Get a couple of horns here. Alrighty, so the horn should kind of line up. Alright. Posterior columns are found in the posterior aspect of the spinal cord, and they form columns along the entire spine. There is an organization to the posterior columns. We take 1/2 of the pie here. Cervical is going to be the most medial. And we're going to work our way down thoracic, lumbar, sacral. So there's a medial to lateral organization. As the neurons project into the spinal cord, they project to the most lateral portion. Consider these as being very thoughtful. They don't want to inconvenience their neighbors. For example, when you go to the movies, rather than walking across every single seat to sit in the middle, sit at the end. Sit on the outside so you don't walk over everyone else's legs. And that's what these axons are doing as well. So they go to the most lateral portion here. So the cervical neurons are going to hit first. Then as we move down, we'll start adding thoracic, move a little lower, we'll hit lumbar, move even lower, we've got our sacral axons appearing. And that's what gives us our organization here. So we're making a body map, and we're going to maintain that. we project up the posterior columns. We haven't formed any synapses yet. We're not going to synapse until we get to the medulla. The medulla will probably have a few humps, maybe something kind of like that. These are going to project up along the same side here, so we haven't crossed yet. In both cases, the second neuron crosses. So these project up. Depending on where this came from, if it came from the upper limb, it's going to synapse in the cuneate nucleus there. If it came from the lower limbs, gracile. You can remember this, gracile, ground. Your lower limbs are on the ground. So that'll determine where they synapse. Either the cuneate or the gracile nucleus. They project along pathways called fasciculi. So there's the cuneate fasciculus. That's what this is. Let's assume we're going to synapse in the cuneate. The cuneate fasciculus is the pathway in the posterior columns that eventually synapses at the cuneate nucleus. And now we've got our secondary afferent. Primary in the dorsal root ganglion, secondary somewhere in the medulla, either cuneate or gracile nuclei depending on where you are in the body. Upper limb versus trunk and lower limb. From here, now we cross. Here's where we form the medial lemniscus. So these fibers are going to cross over and project up to the contralateral thalamus. They will synapse in the ventral posterolateral nucleus of the thalamus. This is where we find our third order neurons. From here, we then project to the cortex, and that's where the magic of perception happens. So, have a look here. You can see they're preserving their spatial locations for lower limb, upper limb, and face. They're including face here. We'll touch on that later. But that orderly projection of axons, of primary afferents to different secondary afferents, to slightly different tertiary afferents, hits slightly different areas of the cortex, and that's why we have a map. That's the somatotopic mapping there. And this will create our non-painful sensation. Where is my body, and what am I feeling in different parts of my body? It's just 3 neurons. It's also just 3 neurons for pain and temp. And that is the spinal-thalamic tracts. Job to convey pain and temp. Now in this case we're still starting in the dorsal root ganglion. These neurons have free nerve endings. They're going to detect changes in pH. They can detect changes in temperature. And they do respond to some degree to pressure, but it has to be fairly intense pressure. Let's just keep it simple. We'll say pain, that is pH, and temperature. These neurons do not project along the posterior columns. Instead, they synapse locally in the dorsal horn. The secondary afferents are found in the nucleus proprius of the dorsal horn. Primary afferents still in the dorsal root ganglion. Secondary afferents are now in the dorsal horn. The secondary afferent also crosses midline, just like in the posterior column medial lemniscus pathway. So here we'll cross over and project up along the anterolateral pathway. We only care about one of the projections here, but this is my spino-thalamic tract. This also has an orderly arrangement as well, so we're creating a body map. Now let this name work for you. Spino-thalamic. We're going from the spine all the way up to the thalamus. So we're going to bypass the medulla here, no need to synapse there, and go on up to the third order neurons in the thalamus. Now, we're still going to hit the ventral posterolateral thalamus, that's true. We still need to know where we're experiencing pain and temperature, but there's a couple of other targets. The mediodorsal nucleus and these intralaminar nuclei that are kind of spread around. The main point here is that we're hitting additional parts of the thalamus. So we're going to have more widespread effects on the cortex. So my third order neurons are still in the thalamus. They're just found in multiple regions. Now, the ventral posterolateral nucleus still projects up to the primary somatosensory cortex, so we know where the pain is. Now, the thing about pain is that it doesn't feel very good. That's created by the mediodorsal nucleus, which projects to the limbic system. The limbic system is a collection of brain regions involved with memory and emotion. So the emotional aspect of pain is created through that mediodorsal nucleus projection to the limbic system. Primary somatosensory cortex is just all about location. Another thing about pain is that it gets our attention. It wakes us up. And the intralaminar nuclei project diffusely throughout the cortex to wake us up. If you are in pain, it's not a time to be drowsy. And so by projecting to the intralaminar nuclei and thus widely exciting the cortex, pain primes us for wakefulness. Pay attention, get away from the pain. Collectively, these three thalamic nuclei affect different parts of the cortex to produce all the different aspects of painful perception. We know where it is, we don't like it, and it gets our attention. So those are our two conscious tracts there. Now let's move on to the non-conscious tracts. Now, it might be helpful for you to try to organize those two conscious tracts into a table, noting the location of the primary, secondary, and tertiary neurons, noting which neuron crosses, it's always the second one. And that might make it easier for you to learn these pathways because they are quite similar. Yes, they have different locations for their secondary afferents, but the primary afferents are all in the dorsal root ganglion, and the tertiary afferents are all in the thalamus. Yes, the spinal thalamic tract has additional targets in the thalamus, and that's an important distinction between pain and non-painful stimuli. Now, the non-conscious tracts are going to include the other components of the anterolateral pathway, as well as the spino-cerebellar tracts. These all share in common the fact that they do not reach the cortex, and as such they do not enter our conscious awareness. But they will do different things for us. Let's visit that anterolateral pathway. So we've got some kind of a pain sensing neuron over here in the dorsal root ganglion. That's going to project in to my spinal cord here. Synapse locally in that dorsal horn there in the nucleus proprius. This secondary afferent crosses midline and projects upward. Yes, we'll reach the thalamus, that's all true. But along the way, there are going to be offshoots or little collateral projections that are going to hit different targets. In fact, we do synapse in the medulla, just not in the cuneate and gracile nucleus. Instead, we synapse in the inferior olive. All right, let's see if I can get a medulla on here again. Not very good at drawing my medullas. Okay, close enough. So pyramids on the front, and then there's a little bump around those called the olive. It kind of looks like an olive, not that much like it, but kind of. So the spino-olivary tract tells you it rises in the spine, ends in the olive. The olive, as we'll find out in lecture 13, has strong excitatory projections to the cerebellum to aid in motor learning. What's the idea here? Let's say you experience some kind of pain because you fell down. You're learning how to walk, and that pattern of movements that you carried out that made you fall down and get some pain in your butt stimulates the spinal olivary tract, so the olive can project back to the cerebellum, which I'm not going to draw here, to affect motor learning. Hey, don't do that again. That's how motor learning works. It's never, this is what you should do. It's always, don't do that again. It's learning your mistakes and not repeating them. And so the spinal olivary tract allows pain to instruct motor programs. How should we stand up? We should stand up in a way that doesn't make us fall down and hurt our butts. Going up a little bit along the medulla pons, we have a number of projections. Let's see, I don't know, maybe we'll get us a big pons or something like that. Okay, we're going to project to the reticular formation. This is a big collection of nuclei that are involved with arousal. So we'll just do some dots here. This kind of projects all along the brainstem, but this is my reticular formation. What this does is project upward to create consciousness, to stimulate the cortex. So this is another way that pain stimulates arousal, besides the spinal thalamic projections to the intralaminar nuclei. So we've got the ascending reticular activating system or something like that. So spino, reticular. Up in the midbrain, we have two projections. I'm going to get this thalamus out of the way here. Okay, so a couple of cerebral peduncles and a couple of lumps on the back. Okay, close enough. Should be a hole here, some gray matter around it. Alright, a couple of projections here in the midbrain. That projection to the periaqueductal gray, which we'll touch on again, spino-mesencephalic. From the spinal cord to the midbrain, and then there's the spinotectal. This is going to target the superior colliculi, so we move our eyes toward wherever there's pain. The spino-mesencephalic tract stimulates the periaqueductal gray, and this is going to play an important role in modulating pain. So we're going to come back to this. Just keep in mind, those anterolateral tracts have a number of offshoots. This will continue up out of the board and finally hit the thalamus. But before we hit the thalamus, there are a number of other things that pain is doing for us. Guiding motor learning, waking us up, changing our gaze, and also potentially stimulating some pain-reducing pathways so pain doesn't get out of control. Now those don't make it to the cortex, so people don't generally know about them. So they're not one of those two really important pathways. The other non-conscious pathways involve the cerebellum. There are 4 spino-cerebellar tracts, and we can divide these in half. Half of these, so 2 of these, deal with nonconscious proprioception. So we could, I suppose, make a little 2x2 table to organize these. We'll think about the function on top. So where is my body? Proprioception. The other tracts are concerned with current movements. So where is my body now? Where will my body be soon? Present tense, future tense. But it's all about knowing body position so that we can appropriately plan our movements to get our bodies where we want them. And that's the job of the cerebellum. Put your body in the right place. Ensure that you can move your hand actually in a straight line. Well, in order to move my hand in a straight line, I need to know where all the other parts of my body are between my hand and my trunk. That involves knowing where everything is now and where everything is finna be. Now we can divide these in half again based on what are we talking about. Are we talking about the arm, or are we talking about the trunk and legs? Because there's going to be two different pathways for those. So, non-conscious proprioception for the upper limb is carried along the cuneo-cerebellar tracts. For the trunk and lower limbs, here we're dealing with the posterior Spino-cerebellar tracts. If we're talking about current movements, trunk and lower limbs are going to be carried along the anterior anterior Spino-cerebellar tracts. And then there's a minor projection for the arms, current movements, called the rostral Spino-cerebellar tracts. Cuneo-cerebellar tract. So those are our four tracts. And they're all dealing with knowing where your body is now and will soon be so we can properly coordinate our movements. Now, the spinocerebellar tracts are all ipsilateral. They deal with the same side either because they are uncrossed, as is the case for our non-conscious proprioceptive pathways, so the cuneo-cerebellar tract and posterior spinal-cerebellar tracts remain uncrossed. These get input from things like spindles, so muscle spindles, Golgi tendon organs, things that are telling me about muscle length and tension. That's my input here. Current movements, I get input from, let's say spinal interneurons. So not the primary afferents, but instead the interneurons that are getting input from primary afferents, but also input from descending motor pathways like the corticospinal tract. My goodness, took a while for that to come up. Okay, let's walk through these pathways here. So over in this slide we have the non-conscious pathways. That includes the posterior spinal-cerebellar tract and the cuneo-cerebellar tract. The posterior spinal-cerebellar tract synapses locally in the dorsal horn, pretty much. It's called the dorsal nucleus or Clark's nucleus, and this runs through the thoracic spine. So the lower limb afferents have to project on upward to synapse there, but those are our secondary afferents. From there, they then project into the cerebellum via the inferior cerebellar peduncles. The cuneo-cerebellar tract does something kind of similar, except it doesn't synapse in the spinal cord, as you can see here. That projects on upward, following along the posterior columns until it reaches the accessory cuneate nucleus. It's just a little outside of the cuneate. Still deals with upper limb though, but in this case not conscious proprioception. Instead, non-conscious. That accessory cuneate nucleus projects along the cuneo-cerebellar tract, eventually reaching the inferior cerebellar peduncles to provide input to the cerebellum. But notice we're all on the same side. So if you look at this illustration, I've bolded the stuff on the right side. It all stays on the same side. It's a little bit different, but kind of the same, for the motor aspect. So what are my current movements? What's going on in the spinal cord right now that's going to affect my body very soon? So it's still ipsilateral, but we're going to double cross. We'll cross once, making us contralateral, and then we'll cross back again, making us ipsilateral. Okay, so the input arises, as you can see in this illustration, from interneurons in the spinal cord. So what's the current chitter chatter? Right, in the spinal cord, we've got that central gray matter. Gray matter is full of neurons and synapses. So there's a large number of interneurons here talking to each other and figuring out how should we properly activate my lower motor neurons. We will talk a lot more. No, we already have talked a whole lot about these, but we'll hit them again in our next lecture as well. But all those interneurons in the spinal cord get some idea about sensory input from primary afferents over there in the dorsal root ganglion. That thing is still here. But also descending input from the corticospinal tract. So these have a good idea of where is my body, where am I going to put my body pretty soon. Inputs from these neurons, so there's neurons within these networks that then project on over. So they're going to cross over and form that anterior spino-cerebellar tract, somewhere all around right here. And they'll project on upward. They're going to head up into the pons, and then they'll enter not by the inferior cerebellar peduncle, but instead by the superior cerebellar peduncle. Crossing over, so there's my second cross. Here's my first, and then when I'm getting into the cerebellum, I get a second cross. So these axons cross over, project up, and cross back, giving us ipsilateral innervation. The upper limbs, similar input, still a bunch of interneurons. In this case it forms the rostral spinocerebellar tract. This is quite small and not well described. It may very well go in through the inferior cerebellar peduncle without crossing, or it may double cross. That's not quite clear in humans at this point. But either way, ipsilateral input for the upper limbs. This is probably good enough to know. Remember, this one double crosses, but all these are ipsilateral. They get different types of input, so they deal with different types of information. They also have their distinct body region. Is it the upper limb or the rest of the body? We have a different tract for those. On to pain. Pain is instructive, but all good things must come to an end, even pain. We need to have some way of terminating pain after we've learned our lesson. And that is where central gating of pain comes in. In this case, we're going to now deal with a descending tract that affects the spinal cord. First, I'm going to walk through it backwards. Then, after we have everything in place, we'll walk through it forwards. And you must walk through this a few times for it to make sense. Please don't just walk through this once. Alrighty, so we start off, of course, with our primary afferents. So out there in the dorsal root ganglion, we of course have our non-painful and our smaller pain-sensing fibers. Free nerve endings for pain, encapsulated endings, no pain. And these will project into the spinal cord. Let's make sure I leave plenty of room here. Alrighty, something kind of like that. I'm going to give myself hopefully a big enough dorsal horn. In fact, I'm going to make this even bigger because there's going to be some things going on here. So, it's not anatomically correct. Okay. So the typical pathway is going to be, right, local synapse for my pain sensing fibers. This crosses over and makes the spinal thalamic tract and the rest of the anterolateral pathway. Now, you've probably noticed that if you experience pain, you can rub the area that hurts and it feels a little bit better. I mean, it's not like morphine, but it feels a little bit better. Well, that's because these non-painful fibers stimulate inhibitory interneurons that inhibit pain. So you bump your knee. Obviously, that's going to activate pain-sensing fibers, but by rubbing it and stimulating these non-painful afferents here, you can inhibit signaling at this synapse in the dorsal horn. So the primary afferents can't activate the secondary afferents as easily, and it dulls the pain a bit. So we have some local inhibition in the dorsal horn that we can get with a little bit of rubbing. That's kind of nice. This is nowhere near as nice, though, as central gating. And so, let's see, we'll inhibit in both places. Okay. Presynaptically, postsynaptically. Okay. But we can do better. We can do better than just rubbing our knee. With central gating of pain, two types of input are going to are going to terminate here in the dorsal horn. There's adrenergic input from the locus coeruleus. This is going to directly act on our pain-sensing fibers. So let's put the locus coeruleus up here, LC. This is adrenergic. These act on alpha-2 adrenergic receptors. You should remember these. If not, that's all right. I gotcha. It's inhibitory. Alpha-2 is GI coupled. So by stimulating these alpha-2 adrenergic receptors on my primary and secondary afferents, I decrease their excitability, and if I am not firing as many action potentials here in my secondary afferent, I'm not going to stimulate the thalamus to say it hurts. So the whole goal here is to dampen down signaling along that spinal thalamic tract. And we can do that with adrenergic input from the locus coeruleus. The other source of input that turns this on is the serotonergic input from the magnus raphe nucleus. The magnus raphe is a fairly large nucleus found in the medulla, a little bit in the pons as well. I'm going to put this below, magnus raphe. Serotonin is what we're releasing here. That serotonin is going to act on excitatory receptors. So clearly we're not going to act directly on the primary afferents. We're going to kind of do what my non-painful fibers are doing. We're going to stimulate an inhibitory interneuron. So here's where we're going to act with serotonin. Let's come on down. We're going to act on this same inhibitory interneuron. We'll act on a couple of sites. We're really going to want to stimulate this thing. We've got good old GQ coupled. Serotonin 2A and C receptors. That is not the most important thing. The fact that it's GQ coupled really matters. We know that's going to be excitatory. It's going to elevate intracellular calcium. Over here we act on some cation channels, the 5-HT3 receptors. I'll write that, but minor point. But we're going to stimulate inhibitory interneurons. That's the point here. And I'll try to clean this up in a little bit. Now the magnus raphe also projects upward to stimulate the locus coeruleus. Unfortunately, it doesn't seem to do it so much with serotonin. Strong activation of the magnus raphe leads to burst firing, and we release neuropeptides. The neuropeptide we release here, in this case, substance P. Substance P acts on neurokinin 1 receptors, which are GQ coupled. Thus they are excitatory. Using this system provides long-lived excitation of the locus coeruleus, so we get a greater amount of adrenergic input. Okay, so we start in the dorsal horn. The locus coeruleus is going to inhibit those primary afferents. The locus coeruleus is turned on by the magnus raphe. The magnus raphe also excites inhibitory interneurons. Okay. Now, substance P you might have heard of before as actually inducing pain. Sure, it can elsewhere, like down here, but up here, no. We're actually inhibiting pain. Okay, let's look at the top graph over there, and what you're looking at is mechanical allodynia. The y-axis is showing you how much pressure they had to put on the paw to make the little rat withdraw its paw. The more pressure you can apply, the less pain they're feeling. However, if they're sensitive to pain, low pressure is enough to make them withdraw their paw. In the top illustration, V1 is baseline, and then they're showing you 5 minutes or 15 minutes after injecting substance P into the locus coeruleus. So they're doing a local injection here. Not just everywhere. Locus coeruleus is getting the substance P. So if you look at the white lines, you'll notice at 5 minutes afterward, hey, we need a whole lot more pressure for them to withdraw the paw. They're not feeling as much pain. It's because of this. Those primary afferents can't easily excite the secondary afferents, so you need a whole lot more pressure to overcome that inhibition. We don't see the same thing, though, if we also apply a neurokinin 1 antagonist. So if we block the substance P receptor, substance P doesn't help us. Cool. This shows us that the effect of substance P is indeed specific to its receptor. It's doing what we think it's doing. Look below there. Same idea, okay, but now they're going to inject still substance P in the locus coeruleus, but then intrathecally they administer an alpha-2 receptor antagonist in the spinal cord. So, great, substance P in the locus coeruleus turns it on. Is it that the locus coeruleus directly inhibits the spinal cord? Yes, that is indeed what it looks like, because if you give that substance P in the locus coeruleus and at the same time inhibit the adrenergic receptors in the spinal cord, that substance P doesn't give you any mechanical allodynia. So those are just some data showing you that this mess is legitimate. Okay, so what turns this mess on? Well, that would be the periaqueductal gray. should really practice drawing this. Okay, I'm trying to draw a midbrain, so you can probably do it better. Okay. There's my periaqueductal gray. Remember that thing? I hope that's in the frame. Okay, spino-mesencephalic tract. Turns on the periaqueductal gray. Periaqueductal gray projects to the magnus raphe, and oh, we've completed the circuit. Isn't that nice? So pain will eventually help turn itself off, because pain stimulating the spino-mesencephalic pathway is going to start to kick on this machinery. And given some time, we can indeed inhibit pain so it doesn't feel quite as bad. Of course, healing of any damage, decreasing stimulation of primary afferents also helps reduce pain. But you've probably noticed if you have an itch and you don't scratch it, it eventually stops itching. Here's why. However, if you scratch that itch, it will continue to itch. You've got to give this thing time. Don't go scratching it, providing that little bit of short-lived local inhibition. Have some patience. Give your midbrain and your medulla a little time to work for you. Now, there are other things that stimulate the periaqueductal gray besides the spino-mesencephalic tract. Enkephalin is an important stimulator. Now, enkephalin binds to mu-opioid receptors, which are inhibitory. But here's the deal. In my periaqueductal gray, well, this is just a mess. I'm going to get rid of this, and we're going to redraw this eventually in a much cleaner box form. My periaqueductal gray has inhibitory interneurons that chronically inhibit the projection neurons that stimulate the magnus raphe. This is where enkephalin, or morphine, will act. These have my mu-opioid receptors attached to them. So if I have some enkephalin, that'll stimulate the mu-opioid receptor, which inhibits this neuron, so it no longer inhibits this excitatory neuron. So now it's free to fire, deliver some glutamate, and turn on the magnus raphe. From here, we excite the locus ceruleus, and we excite some inhibitory interneuron that blocks primary and secondary painful afferents. So these nociceptive fibers here get inhibited via this inhibitory neuron, and they're also inhibited by adrenergic input from the locus ceruleus via those alpha-2 adrenergic receptors. Here, 5-HT2A and C. I might as well. So, opioids disinhibit the periaqueductal gray, allowing this machinery to get turned on. Opioids also act in the spinal cord. We also find mu-opioid receptors on nociceptive afferents. I'll just put them here too. These are still GI coupled. That means they're going to be inhibitory for neurons. So you could get opioids, of course, exogenously, or endogenous opioids like enkephalin. Enkephalin is derived from these inhibitory interneurons. If they burst fire, why might they burst fire? Because they get strong excitation from metabotropic receptors. In other words, the magnus raphe is providing strong input. to these inhibitory interneurons. Yes, they'll dump a little glycine, but when they're burst firing, they also dump enkephalin. And so by dumping out enkephalin, we stimulate mu-opioid receptors and inhibit this synapse. So no matter what's going on out here in our body, none of that pain actually makes the jump to stimulate the secondary afferent. And if we don't do that, we don't stimulate the thalamus. And if we don't stimulate the thalamus, we don't feel pain. Here's another little summary of this whole circuit that I've drawn out for you. Those purple neurons are the pain-sensing nociceptive afferents. You'll notice we have inhibition occurring at multiple sites here. Yes, the locus ceruleus does inhibit serotonergic input from the raphe. That's just some good old negative feedback. But what you'll notice is that the green adrenergic arrows are inhibitory, and they're inhibiting those purple arrows. No pain. The excitatory blue serotonergic input has to act via the inhibitory interneuron. When that burst fires, not only is it releasing a little GABA and glycine, but it spits out enkephalin. Enkephalin provides long-lived inhibition of the nociceptive afferents. And that's central gating of pain. I hope that wasn't too painful, but if it was, leave some questions in the questions box so I know what to address in class. See you later.